Hi there. So what I'm going to do now is actually combine 3 sections into one video. So while you're watching this video, please know that I'm actually going to be incorporating sections 4.1, 4.2, and 4.3. They all relate to using the derivative, especially in regards to graphing and looking at various characteristics of our functions using the calculus that we've learned. Okay, so I will tell you when I'm doing particular sections, but again, this is just going to be one longish video. All right, so my first part to talk about are what we call local max and min. Okay, now a lot of the things that I'm going to be bringing up here are actually things that we discussed in chapter 2, but what we're going to do now is formalize them now that we know how to take derivatives and how we can use them. So let me first start out by just motivating this by saying let's consider one of our very favorite functions to refer to, y equals x squared. And let's talk about this and relate this to what we know about our derivatives. Okay, well, first off, we can compute the derivative. The derivative is 2x. And I claim that if we want to know what our derivative is at any of these values when x is less than 0, well, clearly if I plug a negative number into my derivative, I'm going to have a negative derivative. Okay, and again, that totally jives with what we know about our functions and the derivatives in the sense that when our derivative is negative, it's the slope of our tangent lines, and we see that our function is decreasing. And in a similar manner, if I take any number greater than 0 and plug it into my derivative, I definitely see that my derivative is going to be positive, and that certainly links up to the fact that my function is increasing. Okay, so you need to recall from chapter 2 that one of the things that we saw is that a function is increasing on an interval if and only if the first derivative is positive on that interval. And in a similar manner, we know that our function is decreasing on an interval if and only if our derivative is negative on that interval. All right, so again, this completely links up to what we're already familiar with. Now let me say one other thing. Let's take for example, our cubic function. Okay, we know what the graph looks like. I always call that my John Travolta function from that, my humble opinion, terrible movie from the 70s. But anyhow, what we have is we have y equals x cubed. I think you'll grant me that this function is increasing everywhere. And if I take my derivative of x cubed, I get 3x squared. Now, for any value of x that I plug into my derivative, it's always going to be positive because I'm squaring it. So again, we see that our derivative is positive everywhere, as also our function is increasing everywhere. Okay? Now, in general, when we have a function, okay, well, what do we see? We see that our function is increasing here, we see our function is decreasing, and then our function is increasing once again, okay? Now, I claim that these points here, which we already know are where our derivative is equal to 0, again, it's where it's changing from increasing to decreasing or decreasing to increasing. What I'm going to tell you, though, is I'm going to call this guy a local maximum. And I'm going to call this point a local minimum. Okay? Now, why do I call them local max and local min? Well, when we talk about local, we're talking about in that region versus global, which means everywhere. I claim there is no global maximum because we see that our function goes off to positive infinity. However, in this region, locally, this is my maximum value. And what's happening here? Well, what's happening is my derivative is 0, and that's also where my derivative changes from being positive to being negative. Similarly, locally, in other words, in this region right here, this is my minimum value, okay? We call these also turning points. Now, globally, he's not my minimum because, again, my function goes down to negative infinity. So, what's interesting about these particular points? Notice, those are where, for example, here, my derivative is equal to 0. So what I'm going to do is I'm going to formally define a few things, and then we're going to play around with these concepts. Okay? So, a function has a local maximum or minimum at a point x equals c if, well, it has a maximum if my function value at c is greater than or equal to all function values for all x near c. And it has a local minimum. Well, since minimum is put in parentheses there, I'll put it in parentheses here. If my function value at c is less than or equal to all my function values for all x near c. So that's what we mean by a local max and a local min. Okay? Now, the question is, or the point that I want to make first is that notice on one side, when you have a local maximum, your function is increasing. On the other side, it's decreasing. And similarly, at a local min, on one side your function is decreasing, and then on the other side, it's increasing. Okay? Now, what we just saw with the graph that I had over here is our derivatives at the local max and local min were actually precisely where equal to 0. That's precisely where my derivative is equal to 0. So what I want to do is I want to write a definition here. And I'm going to tell you that a critical point of a function is a number which we'll call C in the domain such that either my derivative is equal to 0 or my derivative at that point, I'm going to write DNE, that's short for does not exist. Now, in this class, we will not be encountering where our derivatives don't exist, but I will show you one quick example here. Is on my absolute value function at x equals 0, my derivative does not exist. So here f prime of 0 does not exist. And one characteristic when we look at graphs to tell where our derivative doesn't exist are sharp corners. Okay, so again, we're not going to be running into that in this class, but you know, for the sake of completion and your notes, I do need to state that. All right, so what I'm going to do now is write down a couple tests that we use, and then what we're going to do is play around with some examples. Okay, so we have what's called our first derivative test. In other words, if we find a critical point, which we can do, because the way you find a critical point is just take the derivative and set it equal to 0 and solve, okay? So what these tests bring out is, let's characterize our critical points. Are they local maxes? Are they local mins? And sometimes our critical points are neither local max nor local mins. Okay, so our first derivative test says, suppose C is a critical point of a continuous function f of x. Okay? And this says if f changes from increasing to decreasing, which is equivalent to saying, in other words, f prime changes from positive to negative, then f has a local max at C. Again, if my function's going from increasing to decreasing, that's going to be a maximum value. And similarly, if my function changes from decreasing to increasing, in other words, my derivative changes from negative to positive, then f has a local min at C. And again, this makes sense. If my function's going from decreasing to increasing, this is going to be my local minimum. Okay? Now, we also have what's called our second derivative test, and I'll write that up on the board, and we will use that now and again as well. Personally, I tend to use my first derivative test. But what our second derivative test tells us is, again, we're going to suppose C is a critical point of a continuous function f of x. And the second derivative test what that tells us is as follows. If when you plug that critical point into your second derivative and you get a positive number, now what do we know about the shape of the graph? We know that it's concave up. I'm just putting it in parentheses because that's sort of a side note at this point. Okay? But if when we put our critical point into our second derivative and we get a positive number, what that tells us is that we have a local min at C. And similarly, if when we plug our critical point into our second derivative and we get a negative number, and yes, again, we know that it's concave down in that region, then what we do is we have a local max at C. Now, you might wonder why this is the case. Well, I think you'll grant me that if you have a positive second derivative, we know that our graph is concave up, whether it's increasing or decreasing. Okay, but clearly, what do we have? Well, if it's concave up, then near C, notice all of your tangent lines are positive. In other words, your graph is actually lying above your tangent lines. So there's no way that it can be a maximum value. And in a similar manner, if you have a graph that's concave down, okay, and when you plug that critical point C in, it has to be a maximum value because notice all your tangent lines are lying above your graph. Okay? So what we're going to do now is play with the ideas of a local max and local min. You'll see how these problems arise and how they make sense with everything that we've been doing here. They're really cool. Okay, and you're going to see how powerful the calculus is when it comes to the graphing. So what I want to summarize right now, while we're writing down our first example and working through our first example, is this. By taking your first derivative and setting it equal to 0, you're going to find the critical points, okay? Those are possible local maxes or local mins, although they don't have to be. I'll show you an example of such. Okay, so we're going to be taking our first derivative, setting it equal to 0. And what this is going to show us is where our function is increasing and decreasing. Okay, so let's, for example, take y equals x cubed minus 3x squared minus 9x plus 2. Okay, now I'm going to take this example a step further just because I can't help myself. What I want to show you is how cool the calculus is, because once we take our first derivative and find our critical points and characterize them, we can essentially get a really decent graph of this function already. Now, I always take a step back when I write down a polynomial function and I say, okay, this is a third-degree function. So from my algebra, I know that as x gets very large and as x gets very small, one arm is going to go up and one arm is going to go down. Okay? Now, another thing that I always do is find, when I have my polynomial functions, is I always find my y-intercept. That's a really quick point that we can get because plugging in x equals 0 is not a difficult step. For example, if I plug in x equals 0, I think you'll grant me that 2 comes out. Now, all we really want to do here is find and characterize the critical points. And like I said, I'm going to take this a step further. You'll see why, because it's super cool. So, how do we find our critical points? What we do is we take our first derivative, which we can do. We get 3x squared minus 6x minus 9. And then we take that derivative and we set it equal to 0. This is where our factoring comes in. You'll see that factoring comes in a lot in this chapter. Okay, I can certainly pull out a 3, and I'm left with x squared minus 2x minus 3 equals 0. And then I see that this is a nice and sweet guy to factor. We need two numbers that multiply to -3, add up to -2. And now I can use my property of 0. I've got the product of 3 things equal to 0. So therefore, at least one of them must be 0. Clearly, the 3 is irrelevant. What makes x minus 3 equal to 0? When x is 3. And what makes x plus 1 equal to 0? When x is -1. Okay? So, 3 and -1 are my critical points. We found our critical points. So now what we need to do is characterize them. So let me show you the steps that you go through. Now this might seem like a lot at first, but once you start going through these steps, you'll see that they become very routine. Okay? What you do is you put these points on a number line. Okay? I'm going to use my first derivative test. Now, I know from my first derivative test that if my derivative changes from positive to negative, I have a local maximum. If my derivative changes from negative to positive, I have a local minimum. And if my derivative doesn't change signs, then it's still a critical point, but it's neither a local max or a local min. So, what I'm going to do, and I always take I always take my test points and plug them into my factored form. Now, when I take these test points, I don't really care what number comes out. All I care is the sign of the number. So, what I'm going to do is take a point in each interval. First thing I'm going to do is take a point less than -1. Doesn't matter whether you take -2 or -1,000. Okay? I'll test -2. And notice my 3 is positive. He's not going to affect the sign of anything. If I plug -2 into this term, it's going to be negative, right? -2 minus 3 is -5. And if I plug -2 into this last term, it's also going to be a negative. And a positive times a negative times a negative is positive. So already I know that when x is less than -1, my function is increasing. Why? Because I have a positive derivative. All right, in here, I'll test 0. I test 0 whenever I can, just because it's an easier guy to plug in. Notice again, the 3 is positive always. If I plug 0 into my first term, I'm going to get a negative. If I plug 0 into my next term, I'm going to get a positive. So therefore, this is negative. All right, notice my derivative changed from positive to negative. That tells me that -1 is a local maximum. Okay, let's see what happens when I'm greater than 3. We'll test 4. And again, if I plug 4 in my first term, it's positive. If I plug 4 in my next term, it's positive. And in the last term, it's positive. So check it out. My derivative went from negative to positive. In other words, my function went from decreasing to increasing. Therefore, we have a local min. Now, given what I asked us to do in this exercise, we're done. But I want to show you how much information we have, because we can already give a really good idea as to what this graph looks like. So, I know, for example, that -1 is a really important value. He's a local maximum, as is 3. He's a local minimum. I also know that the graph goes through 0, 2. We found that. Now, I'd like to get an idea as to where this graph lives. Okay, I know this guy's going to be a local maximum, so it's probably going to go like this, but I don't really know how low it goes or how high it goes at -1. So, how can we determine where it is? What we do is we find our function values at those two places. All right, well, I can plug -1 in here. I have -1 cubed minus 3 times -1 squared minus 9 times -1 plus 2. So what do I get? -1 minus 3 plus 9 plus 2. So we get 7. So not a lot bigger, but about right there. And now let's do the same thing for plugging in our other critical point of 3. So what do we have? We have 3 cubed minus 3 times 3 squared minus 9 times 3 plus 2. Well, these guys cancel out, and so I claim you get -25. Okay, this is not drawn to scale, but I don't think people would appreciate me drawing on the wall here to label a point. But I claim we've got the graph. Why? Because we know when we're less than -1, our function is increasing. He's a local max, so he's going to go down here, and oh, we got a local min, and he's increasing. Isn't that super cool? All right, so let's do this for just a couple more graphs, and then we're going to introduce something else. Okay? One quick one that I want to show you is our cubic. Okay, we've already determined that this function is increasing everywhere, but I want to show you how it looks when your critical point is not a local max nor a local min. Okay, so if I asked us to find the critical points and characterize them, what we would do is we would take our first derivative, we would set them equal to 0, and we'd say, oh, x equals 0. Okay? So pretending that we don't know what this graph looks like, we found our critical point, but what we need to do now is characterize it. So, following the same procedure we just did, we put 0 on a number line, and now what we need to do is take a test point in both of these intervals to see what happens. Where do we plug the test points in? We plug them into our first derivative. So if I plug in, say, -1, once you square it, he's positive. if I test, say, +1, again, when you square it, it's positive. So you see how it didn't change signs, and therefore, while we know that 0 is a critical point, he is neither a local max nor a local min. Okay? Now, one of the things you'll see is he does take on some other meaning with this graph. We'll see that momentarily. All right, so now what I would like to do is another example of this. Okay, so what we're going to do is we're going to find and characterize a couple other critical points for some functions. So the next example that I would like to do is as follows. Yes. So suppose g of x is x e to the negative 3x. Okay? Well, what we want to do is find and characterize our critical points. Okay? Now, notice we're looking at this function and we need to take our first derivative. Check it out. I've got a variable here, I've got a variable here. Therefore, I know that I need to use my product rule. And when we take the derivative of the second term, we need to use our chain rule. So let's first take our derivative and then we'll clean it up and set it equal to 0 and solve. Okay? So it's the first times the derivative of the second plus the second times the derivative of the first. All right, got the derivative done. So I'm just going to write it a little nicer. So it's negative 3x e to the negative 3x plus e to the negative 3x. And in order to find our critical points, we need to set that equal to 0. All right, what should we do here? Well, let's factor. Both terms have an e to the negative 3x, so I'm going to yank him out. In my first term, if I pull out the e to the negative 3x, I'm left with the negative 3x. In my second term, if I pull this out, I'm left with the 1. All right, got the product of two things equal to 0, so we can say, well, either our first one is 0 or our second one is 0. But this guy is never equal to 0. Remember, we have a horizontal asymptote at 0, but this is never actually equal to 0. So, while maybe you stressed out looking at this initial problem saying, oh my goodness, there's an exponential function, it actually doesn't come into play at this point. All right, so we can solve this guy, and I think you'll grant me that we get x to be 1/3. So we have one critical point here, and now what we need to do is characterize this critical point. Well, in order to characterize the critical point, remember I always take my factored form. You put your critical point on the number line, and then what you do is you take a test point in each interval. So, again, whenever I can test 0, I'm all about it. I'm going to test 0 over here. Well, if I plug in 0 here, anything raised to the 0 power is 1, so that's positive. If I plug 0 in here, I get a positive. So, I know that when x is less than 1/3, my function is increasing. So let's take any old point greater than 1/3. Why don't we just test 1? Well, if I plug in 1 into my first term, I have e to the negative 3rd power, which is 1 over e cubed, which is really small, but he's still positive. And if I plug 1 into my second term, I get a negative. And a positive times a negative is a negative. So since this changed sign from positive to negative, what do I have? I have a local max. Pretty cool, huh? All right, so one more example that I want to show you here kind of has you think in a little bit different of a direction. Okay? So, what I'm going to do right now is show you this graph. Okay? But I'm going to tell you that this is the graph of f prime of x. Okay? So what I'm showing you right now is the graph of the derivative of some function f of x. Okay? So here's what I want us to do. What I want us to do is on this graph locate and characterize the critical points of my original function. Okay, so it's really important to know that this is the graph of my derivative function. Okay, so let's ask ourselves what's going on here. Well, we want to find the critical points of our original function. So let's ask ourselves, how do you find the critical points of a function? Don't we take the derivative and set it equal to 0? In other words, we know that the critical points are where our derivative is equal to 0. So let's go on over to this graph and ask ourselves, where are my values, function values, derivative function values equal to 0? I claim right here, and also right there. Okay, that's precisely where my derivative is equal to 0. All right, well, let's use the ideas of our derivatives in the local max and local min. Doesn't my derivative here go from negative since it's below my x-axis to positive since it's above my x-axis? Sure does. So if my derivative is going from negative to positive, doesn't that tell me that my function's going from decreasing to increasing? And if that's the case, that's a local min. All right, let's check out this next critical point. Notice here my derivative is going from positive, so my function is increasing, to negative, so my function is decreasing. And therefore here I have a local max. And last but not least, this value over here. Notice my derivative's not changing signs. It's going from negative to negative. Therefore, while this is a critical point, it's neither a maximum nor a minimum. Okay? So, what we've talked about so far here is the fact that we can use our first derivative to tell us what's happening to our function. In other words, where is our function increasing and where is our function decreasing. Now, our next topic is going to tell us the shape of the graph. And remember, when we talk about the shape of the graph, we're talking about the concavity. So I'm going to have you recall a few things. Now, these inflection points come out of section 4.2. But one of the things that I want to remind you of is we saw from chapter 2 where our second derivative is positive, our function was concave up. And where our second derivative is negative, our function is concave down. So, just like we had a name for the points where our function was changing from increasing to decreasing or decreasing to increasing, our critical points, we have a name for the points where our function changes concavity. In other words, changes from concave up to concave down. And those are what we call inflection points. Now, in a similar manner, notice just like our critical points were where our first derivative was equal to 0, because that's where it changed from positive to negative, negative to positive. Well, notice we're talking about where our second derivative changes signs. So our inflection points we find by taking our second derivative and setting them equal to 0. Okay, so possible inflection points which again is where the graph changes concavity, are where the second derivative is equal to 0, or again, there is the possibility where it doesn't exist. Okay? So we're going to take what we just did with the local max and local min, and we're just going to build on it. So what I'm going to do is now write down a different function. I'm going to take x cubed minus 3x plus 10. And I want us to, for this guy, find and characterize critical points and inflection points. And what we're going to do is we're going to do this for a few different functions. All right, so to begin, what do? Critical points. Take your first derivative, 3x squared minus 3. All right. What do to find our critical points? We take our first derivative and we set it equal to 0. And we can certainly factor this. We can first pull out a 3. And then we see we have the difference of 2 squares. That factors to be x plus 1, x minus 1. Now notice I have the product of 3 things equal to 0. I think you'll grant me that this 3 is not at all relevant. What makes this first guy 0? -1, and the second one is +1. So we have found our critical points to be positive and -1. Let's characterize them. Okay? Well, what do? In order to characterize your critical points, you plug them in your first derivative. So to find function values, you plug them in your original function. To find and characterize the critical points, you plug it into your first derivative. And to find and characterize inflection points, you plug them into your second derivative. That's really an important link to make. All right, I am going to write my factored form right above. And let's take a test point. Over here, I'll test -2. Well, 3 is always positive. If I plug -2 in my first term, it's negative. In my second term, it's negative. So this whole thing is positive. All right, let's test 0 here. Again, the 3 is always positive. If I plug 0 in here, it's positive. If I plug 0 in there, it's negative. Whole thing is negative. What do we have here? We have ourselves a maximum. All right, let's see what happens at 1. Well, again, I'll just test +2 for balance purposes. I got a 3, which is positive. If I plug 2 in here, it's positive. If I plug 2 in here, it's positive. And sure enough, we've got a minimum there. Our function goes from decreasing to increasing. All right, so that builds off what we were just doing. Now, let's find inflection points. How do you find inflection points? You take your second derivative. So, notice my first derivative was 3x squared minus 3. Let's take this derivative. What's the derivative of 3x squared? 6x. And the -3 just is equal to 0. So we can certainly take this guy and set him equal to 0. So 0 is a possible inflection point. Okay? Now what I want to know is, does it actually change concavity? Well, how would we do that? we would do the exact same thing we did with our first derivative test over here. Okay? What does that mean? You take a test point in each interval and you plug it into your second derivative. Well, I think you'll grant me if I take -1 and plug it in here, it's negative. What does that tell me about my graph? It tells me it's concave down. And over here, if I test a +1 and I plug it in my second derivative, I think you'll grant me it's positive, and so my graph is concave up. Isn't that so cool? Okay, so already, I mean, if we really wanted to, we could graph this function. It's going beyond what we asked. But just to get an idea, I can't help myself, sorry. Notice I have an intercept, a y-intercept of 10. So I'm right here. This is not going to be drawn to scale, of that I assure you. And then we have our local max and our local min. So we could get an idea as to what our function values are. So for example, if I plug -1 in here, would you agree I get -1 plus 3 plus 10? So that gives me 12. So just a little bit higher than that guy. And if I plug in a +1, because that's my other critical point, I get 1 minus 3 plus 10. And what do I get out of there? Well, 1 minus 3, -2 plus 10 is 8. So he's still fairly big. This is so not drawn to scale. Sorry about that. All right. So what do we know? Well, the other thing we know is 0 is an inflection point. And we see that our graph on the left side of our axis is concave down, and over here it's concave up. So what do I know? I know that since he's a local max, it's going to be increasing in concave down. Now he's decreasing in concave down. What happens at 0? Well, it's still going to keep decreasing, but notice it changes concavity and he's concave up. Isn't that beautiful? Yeah, I think so too. All right, so let's do this just for one more example, just to get our factoring practice. We're not going to go through and graph everything. Totally do it on your own if you want to. And then I'm going to introduce just one more small concept. So let's just find and characterize critical points and inflection points and all of these fun things. For this guy, suppose now I have x to the 5th minus 5x to the 4th plus 35. All right, well, critical points. Take your first derivative, 5x to the 4th minus 20x cubed. Set it equal to 0. So 5x to the 4th minus 20x cubed equals 0. Sweet, this is a nice one to factor. We can pull out a 5x cubed, and I claim we're left with x minus 4. Notice I have the product of two things equal to 0. What makes this first guy 0? 0. And what makes the second term 0? 4. So 0 and 4 are my two critical points. Now what I want to do is I want to characterize them. So I'll do that right here. Here's 0 and here's 4. Now it always kind of makes me sad when 0 is a critical point, because then you can't test 0, but that's okay. We can handle it. So I'm going to write my derivative right above so that I can just look straight up and know whether it's positive or negative. So over here I'll test -1. If I plug -1 in my first term, it's negative. In my second term, it's negative. Therefore, I know that less than 0, this function is increasing. Between 0 and 4, I can test 1. If I plug 1 into my first derivative, in my first term of my first derivative, it's positive. If I plug 1 into the second term, it's negative. Therefore, I see that in the interval from 0 to 4, my function is decreasing. That makes this guy a local max. Let's see what happens when we're bigger than 4. We can test 5, and I think you'll grant me that if I plug 5 into both of these terms, they're positive, the whole thing is positive, and therefore we have a local minimum at 4. All right, well, what do we have left to do? We've got to find inflection points and see where our graph might change concavity. Well, how do you find your inflection points? What you do is you take your second derivative. So we take the derivative of the derivative, and what do we get? 20x cubed minus 60x squared. And again, it's pretty sweet. We have something that's pretty quick to factor. I take my second derivative, set it equal to 0. In this case, I can pull out a 20x squared, and I'm left with x minus 3. All right, I got the product of two things equal to 0. 0 makes my first term 0, and 3 makes my second term 0. Wow, so 0 is not only a critical point, but it's also an inflection point. So now what I do is I take my second derivative, I take my possible inflection points, and now I test a point in each of these intervals. I'll test -1 here. If I plug -1 into my second derivative, in my first term it's positive since I'm squaring him. In my second term it's negative. So I know that when x is less than 0, my graph is concave down. Let's see what happens when we plug in 1. Well, if I plug 1 into my first term, it's positive. If I plug 1 into my second term, it's negative. So this whole thing is negative. So my graph is still concave down. Notice that 0 is a local maximum, but it does not change concavity at 0. So let's see what happens when we're greater than 3. Let's test, say, 4. If I plug 4 in my first term, it's positive. Second term, it's positive. So sure enough, my graph does actually change concavity at 3. Okay? So now what I would like to do is talk about not only local max and mins, but global max and mins. All right, so what I want to say is that the local max and min gives the largest if it's max, min, smallest if it's minimum in some interval. Okay, so that tells us in that region who's the biggest and who's the smallest. But what if we're interested in finding the largest or the smallest values of our entire function? Okay, as you probably assume, that's what we call our global max and our global min. So for example, you have a global max or a global min at a point C if, well, it's a maximum if your function value at that point is greater than or equal to all of your function values, so for all x, and it's a minimum if your function value there is less than or equal to all your function values for all x. So notice local, it was for x nearby. Global, it's for everybody. Now, a reasonable question to ask is, how do you find such? I mean, you know, we're thinking about our polynomial functions. defined on this whole thing, there is no largest and smallest value because it goes on forever in both directions. So this gets infinitely large and this gets infinitely small. So, you know, in a function like this, we say there is no global max or global min. Okay? Now, it turns out, though, that you can talk about your global max and your global min if you're talking about it on a closed interval. So let me write this out. In other words, we've got to cut off this function somewhere and say, okay, we're only looking at it on this interval. Now, where is my global max and my global min? Well, I think you'll grant me that this is my global max. And right here, this is my lowest point of it all, is my global min. Now, something I want you to notice, this is a local min. Notice my function's changing from decreasing to increasing. So in this example, my local min and my global min are one and the same. Notice over here, I have a local max, changes from increasing to decreasing, but in this case, my local and global maximum are different. So it turns out, oops, need to erase the board before I can write more. It turns out for a continuous function on a closed interval. What do I mean by a closed interval? It means you need to include your endpoints. The global max and min can occur at one of two places. Can occur either at endpoints or at your critical points. Okay? So, in practice, how do we do this? Well, let's take this guy. Let's take this function f of x equals x cubed minus 6x squared plus 9x plus 2 on the interval from -1 to 4. Okay, now let's actually take this guy really far. Okay, what I want us to do is find and characterize our critical points, find our inflection points, and then also find the global max and min. We can do that here precisely because we're on a closed interval. So we're only looking at this polynomial on a certain interval. Okay? All right. And if temptation exists, maybe we're even going to graph it too. Okay? So let's do this. Critical points. Take your first derivative, set it equal to 0. What's our first derivative? 3x squared minus 12x plus 9. We can set this equal to 0 and solve. What do we get? We have 3x squared minus 12x plus 9 equals 0. Again, we can yank out a 3, and we're left with x squared minus 4x plus 3. And fortunately, due to the example that I picked, we can even keep factoring this. What do we have? We have x minus 3 times x minus 1. So, our critical points are at 3 and 1. So we have critical points at 1 and 3. Let's characterize them. Okay? Well, what do? We take a test point. So over here, you better believe it, I'm going to test 0. If I plug 0, well, the 3 is always positive. This is negative. This is negative. So it's positive on that interval. Now in here, let's test 2 when possible. At least it's nice to test whole numbers. The 3 is always positive. If I plug 2 in my first term, it's negative. In my second term, it's positive. So this is positive. So what do we know? We know that at 1, we have a local max. Let's take a test point greater than 3. How about 4? Well, 3 is always positive. If I plug 4 in here, it's positive. If I plug 4 in there, it's positive. So we have it being positive. Therefore, at 3, since my derivative is changing from negative to positive, I have a local min. Okay, so I'm keeping those in mind because when we find our global max and global min, those are our candidates, 2 of our candidates. Okay, all right. Well, let us now, did that? Check. Let's find our inflection points. How do you find inflection points? Well, we know our first derivative was 3x squared minus 12x plus 9. So to find our inflection points, we're going to take our second derivative and set it equal to 0. So our second derivative here is 6x minus 12. It's pretty sweet to set it equal to 0. I think you'll grant me that we get x equals 2. Well, let's see if our graph changes concavity at 2. What do? You take 2, put it on your number line, and now we take test points in each of those intervals. Okay, let's test 0 here. Remember, you always plug it into your second derivative. If I plug 0 in my second derivative, it's negative, so my graph is concave down. If I plug 3 into my second derivative, I think you'll grant me that it's going to be positive, so my graph is concave up. So 2 is an inflection point, and that's where my graph goes from concave down to concave up. All right, cool. Next, find our global max and our global min. Well, we need to ask ourselves, what are our candidates for our global max and global min? Well, the candidates for them are your critical points, so 1 and 3, as well as your endpoints. Now, how do we know who's the biggest and who's the smallest? Well, isn't that just determined by finding our function values? Sure is. So what I'm going to do is find my function values at each of these 4 points. Again, our candidates for our global max and min are our critical points and our endpoints. Okay? So if I plug 1 into my function, what comes out? Well, what do I have? 1 minus 6 plus 9 plus 2. So negative 5 plus 9 is 4 plus 2 is 6. So I know that the ordered pair 1, 6 lives on my graph. Let's take 3 and plug it in. What do we have? We have 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2. And if I plug 3 in, well, what do we have? We have 27 minus 54 plus 27. Oh, I love it. Notice these guys all cancel each other out. We just get 2. So now I also know that I have the ordered pair 3, 2. And again, we know that he's a local max, local max, and we know that this guy here is a local min. All right. So we got two ordered pairs. Now let's see what happens at -1. Well, if I plug -1 in, what do I have? Well, you cube it, you get -1. Then we get -6, -9, plus 2. So what, -16 plus 2 is a -14. So I also have the ordered pair -1, -14. Looking pretty small here. Let's see what happens at +4. Okay, if I plug +4 in, what do I get? I get 4 cubed minus 6 times 4 squared plus 9 times 4 plus 2. So what do we get? We get 64, and 4 squared is 16 times 6 is minus 96, plus 36 plus 2. All right, so 64 plus 38 is 102 minus 96, so we're going to get 6 out. So now we also have the ordered pair for 6. I'm going to erase all this. Okay, so what is our global maximum? Oh, cool. Our global maximum actually occurs at both, our global max is 6. That's our largest function value on this interval, and it occurs at 1 and at 4. So that's our global max, and our global min is -14, and that occurred at -1. So something sort of cool is we could actually graph this function on this interval. Notice we're going from -1 to 4. What do we know? At -1, we're way the heck down here. At 1, we're up at 6. And at, what else do we have? At 3, we're at 2. And at 4, we're back up at 6. Now, we found that 1 was a local max. In other words, this is one place where it goes from increasing to decreasing. And we saw that at 3 we had a local min, so we knew here our function goes from decreasing to increasing. Now don't forget that we also found an inflection point. We found an inflection point at 2. And what did we see at 2? We saw that at 2, our graph changed concavity. We went from concave down to concave up. Now, it's probably a good idea to know what our function value is at 2, just so we can get an idea here. So if I plug 2 in, I get 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2. So what does that give me? 8 minus 24 plus 18 plus 2. So 28 minus 24 is 4. So right about here. Well, I claim we got it. Okay, my graph is concave up and he's increasing. Pretend this is concave down. Sorry about that. Still concave down, he's decreasing, still concave down, but now it changes concavity, and there we have it. Pretty sweet, huh? Okay, let's change this sort of thing slightly. Okay, I know that this is a lot, you guys. But now what I'm going to do is I'm going to give you some characteristics of a function, and I want you to graph it. Okay? So what if now I want you to sketch a graph of a function on the interval say from 0 to 10 that has a local min at 3, a local max at 8, but it has the global max and mins at the endpoints. Now, you can draw many such graphs that satisfy this. We're just going to draw one such graph. All right, so we know it's defined from 0 to 10. 1, 2, 3. Okay, and what do we know? We know it's going to have a local min at 3. I could draw that down here, doesn't matter. I'll just put them right there. What does it mean to have a local minimum at 3? What it means is my function is going to be going from decreasing to increasing. Okay, I just put that there just as a placeholder. What else do I know? I know that I have a local maximum at 8. Okay, now I could put my local max anywhere, but I'm going to put them up here. It means that my function is going from increasing to decreasing. Okay, now the other thing that I know is that my global max and global min occur at my endpoints. Now notice it wasn't specified that my endpoint of 0 had to be one or the other. So you could actually draw it either way. Just by the way my graph is looking, I'm going to put my global max way up here. So what I'm going to do is draw this graph. So it's going to be increasing really slowly, but then it's going to go decreasing, and now I need my global min to be right there. All right, notice global max, global min, local max, local min. Okay, so let us just do one more example here. Suppose I tell you that the quantity of medication in the bloodstream T hours after ingested is given by this. Q of T is 200 T e to the negative T. And what I want to know first is how much medication is in the bloodstream when T equals 0. And this is an obvious question to answer, but let's compute this, okay? Well, when T equals 0, don't we just plug 0 into our function? Notice we have a 0 here. Let's just pretend this is in milligrams. There's nothing in there, okay? So initially, there's no medication in the bloodstream, which is something that we can intuitively guess. Now, what I want to know then is when is the maximum quantity of medication in the bloodstream and what is that quantity? All right, now we know that when we want to maximize things, what we do is we take our derivatives. So what we're going to do is take our first derivative, q prime of t. What do we get to use? We get to use our product rule here, okay? So check it out. It's the first times the derivative of the second. Notice the chain rule, plus the second times the derivative of the first. So we can write this as negative 200t e to the negative t plus 200 e to the negative t. And how do we find our critical points? What we do is we set it equal to 0. Okay? Well, we can factor out a 200 e to the negative t. And what am I left with here? Well, I'm left with a negative t plus 1. Well, I've got the product of two things equal to 0. Can my first one ever be 0? No, it's an exponential. And what makes this second guy equal to 0? T equals 1. So our candidate is 1 hour. Now, we know intuitively that this is going to be a local maximum. How could you test it? Again, you could take test points on either side of 1, but I think you'll grant me that it's going to go from positive to negative. Okay, now notice you can't really plug in t equals 0 because that doesn't really make sense. So what you're going to need to do is plug in a fraction. Okay, so you could plug in, say, 1/2, and that's fine because 1/2 of 200 is 100, and it's going to be 100 divided by some number. Okay, so it's not bad to plug that in, I assure you. So we've answered the first question. When? Now we're going to ask ourselves, what is that quantity? Well, how do we find that quantity? What we do is we plug it into our original function. We find q of 1. So we have 200 times 1 times e to the negative first power, and we're going to get about 74 milligrams. All right, I know this is a lot, but it's all really connected with each other. So I hope you have a ball playing around with these sorts of things. Thanks.